it's a maximally symmetric manifold. Okay, so the equation is you put in a we will see this again later, but this is one thing you can retain for you at the end of this day. So put yourself in a Minkowski space-time of dimension 1 plus d. Okay? Signature plus minus minus minus. Consider this equation. This is a Lorentzian manifold. Okay? And for reason that I will explain during my talk, one topic, locus, which is extremely important to understand this, the quantum field theory and even the classical field theory on this manifold, and the same will be true also for the anti-de Sitter case, is the cone. The cone has the equation psi 0 square minus psi square equals 0. Okay, it's the light cone in the ambient space. This is the manifold. This is the light cone. I will show the picture better than there. But let's do a little exercise while waiting for the others. Consider this thing, psi, scalar psi. In the sense of the ambient space, this means psi 0 x0 minus the vector part. These are d plus 1 dimensional vectors. And psi square is 0, okay? So it's a vector here. I will explain why one does these things, okay, after. But let's do a little exercise in mathematical analysis here. So this, you take one vector here, take the scalar product in the ambient space sense, and then take a complex exponent of it to the lambda. Okay, it is not very well defined because this can be 0 and negative, but we will take care about the problem after. Okay, so the exercise consists in this: show if you consider the Klein-Gordon operator on the de Sitter manifold. We will do it later. These things are proper function. How you can show this? This is the Klein-Gordon operator on the manifold. So you can do the standard way, choose a coordinate system on that manifold, and then computing coordinates the Klein-Gordon operator, write this thing in coordinates, and verify the equation. Or you can use the Klein-Gordon operator in the ambient space. How do you do this? First, you extend your function as a function homogeneous of degree 0 in the ambient space. You see? This is the function which is at the beginning defined on the manifold, and then you extend in the ambient space by a degree of homogeneity 0. If you multiply this by mu, this by mu, this by mu, this stays invariant. And then you apply the Klein-Gordon operator of the ambient space to this function. You do short calculation, and you verify that these things are eigenfunctions of the Klein-Gordon operator relative to this eigenvalue. These are the objects I will use to construct the theory. Okay, so let me start with the historical we are waiting for you, and while waiting, I said one technical point of the talk, but we will come back on it. Okay, so I think I will use part of the, I will present by using the projector, because I have drawings already prepared. So as I said, here it is, the sitter universe. I will start with an historical introduction, but this is just the geometry. You see, you think of a Minkowski space-time in dimension d+1. Here is the metric. The Lorentz group of the ambient space-time is the relativity group of this manifold. It is left invariant by the Lorentz group of the ambient space-time. And you see that here the group is not the semi-direct product of a translation group times a Lorentz group. It's a group which has no translation invariant, no abelian translation invariance group. This is the source of the technical difficulty here. The source, excuse me?
It still has a Lorentz subgroup.
It depends on what you choose as a point. You choose an origin, and this you call it a Lorentz subgroup. But the remaining part is not abelian. Here is the anti-de Sitter manifold. You see that the anti-de Sitter manifold, you can construct it the same way. Now you consider a space, an ambient space, which has 2 times, 2 plus sign in the metric, and d minus 1 minus sign. So it is not a space-time. But if you consider this manifold, note that there is a plus here, this manifold is Lorentzian. How do you do in practice? You write the geometry of the ambient. I will show an example after of the ambient space, and then you take the restriction to your manifold in very much the same way as you do for a sphere. Write the Euclidean metric of R3, and then you restrict it on the sphere. You do the same thing here. So here is anti-de Sitter. We will see that with those objects we can give a unified presentation of quantum field theory of on such manifolds. But as I said, they are similar but strongly different in that because of the thing we were saying. You see, there's no globally defined time-like killing vector field on the de Sitter manifold. So you see, it's similar to what we saw in the Unruh effect. What you call time on one side of your manifold would be minus the time on the other side. On the other hand, from this point of view, the anti-de Sitter manifold is easier because you have a globally defined time-like killing vector field. The difficulty is that in the anti-de Sitter manifold, this manifold is non-globally hyperbolic for 2 reasons. One, because there is this boundary, a space like infinity. You see, this boundary. This is a copy of a Minkowski space-time. And the second is because the manifold is periodic in time. You can curve the problem of periodicity in time by going to the covering of the anti-de Sitter manifold. But this does not solve the lack of global hyperbolicity due to the presence of these boundaries as space like infinity. And this is the source of the possibility even of speaking about this ADS CFT correspondence, because you will have something which is living in the bulk and which has its legs on the boundary. So the theory which are related from the bulk to the boundary are in some way obtained by restricting the theory to the boundary at infinity. We will see this at the end. So quantum field theory on the de Sitter manifold is more difficult than quantum field theory on the anti-de Sitter manifold, even if this is not globally hyperbolic. Because here you have a global time variable, and so you have a positive energy here. You don't have a positive energy. You don't have the possibility of defining a globally positive energy on the de Sitter manifold. So here comes the historical section of this lecture. I will like to tell you some words on why it was invented, the de Sitter geometry. And as I told before, I made one extended lecture on this thing, which is called La naissance de la cosmologie en tant que science. You can look at it on the YouTube. It was a conference given in Paris, but someone registered it and put it on YouTube. So here are these guys, Einstein and de Sitter, and you know, maybe you know, or maybe you have read the original papers where cosmology was invented. Just after writing his paper on general relativity, Einstein wrote his cosmological paper. It is, so this picture is Einstein and de Sitter, but this is a picture which is, of course, of the beginning of the 30s, when these two guys met again together, and de Sitter was dying soon after. So these are the founding papers. This is the paper by Einstein, in which he invented cosmology as a science. It is translated in English in this little book by Dover. And these are three papers by de Sitter, which were written at the very beginning as an answer to this paper by Einstein. So, as you know, Einstein was a metaphysicist in the sense that he was driven in his own research by metaphysical idea. The very idea of special relativity is in a sense a metaphysical idea, in the sense that even the principle of relativity is not a law of physics. It's a law that the law of physics have to satisfy. When you say that all the laws of physics have to be the same to all inertial observer, you are not speaking about one law of physics. You are speaking about a law that the law of physics have to satisfy. You see, in this sense, it's metaphysics. In the same way, he was considering the cosmological problem as the first application of general relativity, because the general relativity itself was invented to try to cope with this Mach principle. Mach principle, you can summarize it by thinking that the geometry of the space-time has to be completely determined by the position and distribution of velocity of the masses, and nothing else. So the point is that when you try to solve the equation of general relativity, you need to impose boundary condition at infinity. And when you impose boundary condition at infinity, in a way, you are recovering the Newton's absolute space, because the masses are not enough. You need to say something which is external. So in a way, you are again using a principle like the principle of absolute space by Newton. So what was the idea? So there was a discussion between already before between Einstein and de Sitter, and Einstein was thinking of putting huge masses beyond the horizon to solve this problem, but de Sitter told to him, why you do this? Absolute space is more reasonable. There's this strange thing I cannot say. I cannot see in any case. So Einstein convinced himself that the sitter was right. And then he had this crazy idea. And so you can read this, sentence in which Einstein was writing to Ehrenfest. And maybe you know that Ehrenfest was at the center of a seminar he did in the Netherlands, in which all the ideas of general relativity and quantum mechanics were developed. So writing to Ehrenfest, he played a very important role in the history of quantum mechanics and general relativity. He said, I'm again perpetrating something relating to the theory of gravitation that might endanger me to being committed to the madhouse. And what is this crazy idea? Because at that point it was a crazy idea. I have a problem with the boundary condition. No more boundary condition. The universe is spherical. So this is the solution by Einstein to the problem of boundary condition. I consider a spherical universe. And because, so this idea, would have he taken seriously this idea, he would have discovered that the universe is expanding immediately. But since he had this strong prejudge that the universe has to be static, this obliged him to introduce the cosmological constant. The cosmological constant in the cosmological paper by Einstein was introduced because he wanted a spherical universe. A spherical universe was there to solve the problem of boundary condition, but he could not do this. He knew that there were solutions of general relativity non-static having spherical geometry. But since he had the prejudice that the universe has to be static, and this was based on the understanding they had of the sky at that time, the static stars, you see. The galaxies were not yet discovered at that time. So, this is a statement that Lemaitre, which is the actual giant in cosmology, because he himself discovered the Hubble law before Hubble. And maybe you know that probably it is possible that the new space observatory we will call the Lemaitre Space Telescope. Today there is no more doubt about this point, that Lemaitre is the one who really understood cosmology the first. So this is a sentence that Lemaitre wrote in 1948, when at the moment where everyone dismissed the cosmological constant. Still, there were reasons why Lemaitre still considered, when no one else was convinced of the necessity of the cosmological constant, and the argument was about the age of the universe, that you discover something from reason which are no more good, but the thing you have discovered is still good. So the cosmological constant appears because Einstein wanted a universe static and spherically symmetric. And you see, this is the Einstein static universe you know very well, so I don't take time to explain what it is. But one interesting feature of the Einstein static universe is that the radius is related to the mass. The radius of the universe is directly related to the mass through the cosmological constant. So no mass, no universe. This is a practical realization of Mach principles. So it was very glad Einstein because of this result. But then immediately after came the sitter that trying to redo the computation by Einstein discovered immediately a new solution. He was considering again the problem of boundary conditions. I don't explain what is the technical point, but if you read the original papers, this is very clearly explained. So the problem is that even if you don't see it, there is a remnant of absolute space in this solution by Einstein. So there is a boundary condition even here. So trying to get rid of this boundary condition, what he tried is to get a sphere in 4 dimensions. So the very first way in which the de Sitter metric was obtained was through his analytic continuation in 1917. So the Euclidean sphere was there in the first paper by de Sitter. There was no quantum field theory at all at this time, you see. Now we are used to the Euclidean manifold. It's something which is even more too natural in quantum field theory, because people tend to forget that when you start from the Euclidean world to get back to the Lorentzian world, you need certain analyticity property for the correlation function. Otherwise, you stay there. But at that time, it was completely a strange thing. But this is the way de Sitter discovered his own metric. Try to make a sphere in 4 plus 1 dimension. And here is the solution. And this solution is completely anti-Machian in the sense that there is a universe with no mass inside. No mass at all. So it's completely at the opposite of the ideas that Einstein was pursuing while inventing cosmology. So Einstein started criticizing the de Sitter solution. Was unphysical, was wrong, or there were matter inside it. That's why he tried these 3 possibilities, because Einstein, he was very intelligent, as we know, but also his prejudge, which from time to time led him to his enormous discovery, also led him to big mistakes. So here he tried to dismiss the solution as wrong. And in the second paper by de Sitter found a way of writing the de Sitter metric, and you see here you can do it very simply by using the embedding in the 5-dimensional space. I will send you the slides. So these formulas you will have in your mailbox today. So if you try this coordinate system, you can verify it solves the de Sitter equation. And this is describing a portion of the de Sitter space-time in static coordinates. You see, it's very much like a black hole metric. So Einstein was glad with this solution, but this solution, because at that time they had no understanding. So they were trying to understand the geometry through this particular coordinate system. And the Schwarzschild metric has already been written in 1916, but they did not understand the structure of the horizon. So Einstein was led to consider that there was matter indeed in this model. And the matter was here on the horizon. So he was glad because it was false in his understanding that this universe is empty. But this is, of course, not true. And there was a long discussion taking place there. And it's really, really interesting to see also, to read also the letters these people were writing to each other. Because at that time, no internet, people wrote handwritten letters with drawings in them, and they are very instructive. And in our epoch, it's a poor epoch, because these things is lost forever, while we can understand what they were saying, looking at their correspondence. So you see, at the moment, there was other people entering in a discussion, like giant people like Weil or Klein, and Klein finally solved the problem, because Klein understood that it was an embedded surface in 5-dimensional space. There was no singularity at all around, was completely regular, the solution, and all the criticisms by Einstein were defeated, but Einstein still dismissed this solution because it was non-static. Because the universe has to be static, this solution cannot be interesting. So you see, if Einstein had pursued his own idea of the spherical universe and abandoned the staticity, he would have discovered the expansion of the universe just on the basis of this equation. He modified the equation because of his prejudge. So in this particular setting, his prejudge was misleading him, but in the end he discovered the cosmological constant this way. But he didn't like the cosmological constant. He thought it was really ugly. The one who defended the cosmological constant even before its necessity, which was seen in 1997, was Lemaitre. So this is just a summary, but if you are interested, you can look at my talk in Saclay, which you find on YouTube. So now we are today, and this is the understanding we have of the universe. You all have seen the same, so I don't need to comment about the fact that the biggest part of the energy distribution of the universe is on the form of a cosmological constant. So we think today, on the basis of the cosmological equation based on general relativity.
Can I ask a couple of questions?
Yes.
So, can you show again the cosmological Einstein equation with the cosmological constant?
Here? No.
The one that has the cosmological constant.
It will come later. No.
Or before.
It was before?
A little further. Yeah. Well, no, one before.
This one? Or?
Yeah. Okay, so the lambda term is on the left-hand side. It's like an extra term on the left-hand side. It's not like part of matter, which is on the right-hand side.
Okay.
The way it's written like this, it is not part of matter. Of course, you can move it around and take it to the right-hand side and think of it as matter, but there's no reason why it would do that. So why call this thing a form of energy or matter or dark energy when I can just equally well think of it as an extra term in the Einstein tensor?
You can do.
And so why this plot where lambda is put on the same footing as matter, neutrons?
Because it has the form of a stress energy tensor, as you know. Of course, you can say there is a constant in nature, which is lambda. And this is an interpretation. I mean, I don't think it adds very much to the comprehension if you write to the right or to the left.
Then there's this pie chart that everybody shows that has lambda as the biggest part of the energy content of the universe.
Sure.
I just don't get this stuff. Like, if there's a second term on the left-hand side, which is Ricci scalar G mu.
Yes.
Why am I not calling this matter? Take it to the right-hand side and say, oh, this is a Ricci matter.
No, but because when you solve the equation, this is a history, you know. The way of writing things comes from history. The interpretation you give to those things is up to you. The equation like that, it's transparent to the fact that you put it on the right, to the left. But it's sure what you are saying, that there is, in the end, people, even us, not people there, forget that when they are talking about the interpretation of the data that they come from the Planck satellite, they are looking at those data through the spectacles of these equations. So if you change your equations, those data will say different things.
So my question is about the pie chart.
Yes.
What's
in the pie chart, you think of something which is not necessarily the cosmological constant, but it behaves as the cosmological constant, more or less. And this is part of the energy momentum tensor of the cosmological equation. Yes. This is the interpretation, but I can go a little bit further. So if you, this is the interpretation is this. So you know all these things I skip. we will see. So here is the Friedman's equation. So you get in here matter, radiation, cosmological constant, and curvature. So these are the components of this chart. This is the way it is used today as the standard way of looking at what you see in the universe. And you see that if you agree with this, and people seem to agree with this because even 2 Nobel Prizes were given for this thing, you see that not only the cosmological constant is the bigger part today, but it will be bigger and bigger because of the expansion of the universe, this term will drop away, and only the cosmological constant stay if this model is correct, if this interpretation is correct. But it's an interpretation, I agree with you. So what is the question?
Why put lambda on the same footing as energy and matter in a pie chart that says if you think that this thing h square is something that you can measure, h square is this, then even if you put this on the left, on the right, this doesn't change. If you measure h square is this thing. Doesn't matter where you put your lambda. If you say h square is not the right quantity to measure, this is something else, right? No, we can discuss maybe later. So if you agree with this, that this is the most important part in this Friedman equation, then you can say, why don't solving the equation without all these things? So this is not the way it was done by the sitter. And then you have 3 possibilities according to the geometry, even if you put a spherical geometry. So these are the equations in absence of matter, in presence only of the cosmological constant. There are 3 possible solutions. They are all exponential type, of course. But depending on the sign you put here, you get the hyperbolic cosine, the exponential, and the hyperbolic sign with these 3 geometries: spherical geometry, flat geometry, hyperbolic geometry. And so now go back to the idea that the de Sitter manifold is an embedded manifold in the Minkowski space-time, and you make the restriction from the ambient space-time to the manifold by using this coordinate system. This coordinate system, what says? It says this is the time at the same, or else it says spatial sections are spheres. If you say this, I will break this thing. If you say this and you compute the geometry, you get hyperbolic cosine, the one you got by solving. If you say no, the time is not this, is this. So x0 plus x4 is exponential of the time. This is the relation defining the time. With this relation, the spatial sections are planes, are three planes, Euclidean planes. So this is the coordinate system you can construct by hand, just by this ingredient. You take the restriction of the ambient space metric, and you get flat spatial section and exponential of the time. Of course, you see that this coordinate system covers only 1/2 of the de Sitter manifold, but if, as we already did, you complexify this time, this becomes a global coordinate system. It covers also the other half. And then there is also the possibility of having an open universe. Now you take the time this way, these planes, these are, think of this, time is going this way. You do, it is a time also, and you get the hyperbolic geometry, Lobachevsky space. So you see 3 apparently different solutions are just, as you know, as you knew already, but I'm just remembering to you, just different coordinate system on this globally defined manifold, which is maximally symmetric. And from this viewpoint, from the cosmological viewpoint, the de Sitter geometry is the one which allows more possibility.
This is Minkowski space. If you solve the Friedman's equation for Minkowski space, means put lambda equals 0, you get only two possibilities. Either k equals 0, planes. In this case, the scale factor of the universe is 1. So it's Minkowski space in Lorentzian coordinates. Or you put the hyperbolic signature of space, k equal -1, you solve this equation, and then you get A equal T. This is the Milne universe. Milne universe is just Minkowski space when you said that spatial slices of the universe are Lobachevsky spaces. So in the Minkowski case, you have only the flat and the negative curved possibilities. While if you do the same for anti-de Sitter, you just get k equal -1. So for de Sitter, you get the 3 cosmological models. For Minkowski, you can get 2, and for anti-de Sitter, only 1. If you are interested in cosmology, I mean, there are lots of other coordinate systems of anti-de Sitter, of course. But Friedman-Robertson-Walker type, just with negative spatial curvature. It's interesting that the hyperbolic coordinate system for de Sitter, this open model, was already present in the first paper by de Sitter. So in the first paper by de Sitter, you'll find the Euclidean manifold and the hyperbolic cosmological coordinate. There were mistakes in there, but this is not strange because the natural analytic continuation of the sphere goes into this hyperbolic model. So this is describes the coordinate systems people normally use in de Sitter, but there are other coordinate systems which are more adapted to string theory, for instance, that people do not seem to know. I don't know why. So let's go to a more now we go to describe the geometry in a coordinate-independent way. So as I said, the crucial thing is this light cone in the ambient space. The light cone in the ambient space does two things. The first thing is it gives the light cone ordering to the manifold. So what you do, choose one point, draw the light cone of the ambient space in that point. If you look at these shadows, this is the future of this point. This is the past of this point. And this is the region which is space-like with respect to this point. This translates in image this requirement which comes from the embedding in the ambient space. 2 points are space-like separated in the de Sitter manifold if they are space-like separated in the ambient space sense. So you don't need to use coordinate system to understand this. At the same level, also for the anti-de Sitter case, so remember there are here 2 plus sign. The embedding manifold is not a space-time, but when you operate the restriction, this restriction, you get a Lorentzian space-time, and also in this case, the asymptotic cone in the ambient space plays a very important role. You have to know that this asymptotic cone in the ambient space is the conformal, is the covering of the conformal compactification of the Minkowski spacetime. If you do conformal field theory, they naturally live on such a cone with 2 plus sign. This is already known to Dirac. Dirac invented this construction. I think Dirac is the one who used the anti-de Sitter manifold, by the way. I'm not sure of this, but I don't know of any older paper in which you can recognize the anti-de Sitter manifold. And you see, this is the conformal group in dimension D. It acts naturally on the anti-de Sitter manifold, and it acts naturally on the asymptotic cone. The asymptotic cone plays the same role as the boundary. So the ADS CFT correspondence, you can look at it as a correspondence between something which is living on the anti-de Sitter manifold, having this symmetry, SO D2D minus 1, which is the anti-de Sitter symmetry, and something which lives in the asymptotic cone, having the same symmetry. Now you interpret this symmetry as the conformal group. Of course, there is a difference. So the same thing is true. You use the ambient space to characterize space-like separation on the anti-de Sitter manifold also, but the manifold has a local light cone ordering, which is not global, because you can come back going towards the future. So you say this, you can summarize this, saying that the anti-de Sitter manifold is causal, but not strongly causal. I mean, locally, you can do the light cone ordering. If you give a neighborhood of 1 point on the anti-de Sitter manifold, you can make the light cone ordering there. But if you do a whole trip, you come back in the past.
So this is a closed time-like curve?
There are closed time-like curves with the anti-de Sitter manifold, of course. So let's now describe classical motion. Here are the geodesic equations. If you want to solve those geodesic equations in the Sitter or anti-de Sitter, you can do it in any chosen coordinate system. This is maybe easy or not, depending on how clever you do the things. But you can do it in a much simpler way. So exactly because these are spheres, the Sitter, anti-de Sitter, are real sheet of a complex sphere. And you know how you get the geodesics of a sphere. You cut the sphere by planes which go through the origin of the ambient space, okay? And you get the maximal circle. You do the same thing. Here is the de Sitter manifold. Cut the de Sitter manifold with a plane which contains the center of the de Sitter manifold. And these are the light-like geodesics. Time-like geodesics. Light-like geodesics you get when this plane becomes light-like. So the question is, how can we parameterize those geodesics? The same happens in the anti-de Sitter case. Take the anti-de Sitter manifold in this embedding, cut the manifold with a plane which contains the origin of the ambient space, and these are the time-like geodesics. You see, they are closed curves. They meet on the antipodal point. So all the geodesics you throw in the anti-de Sitter case meet again after half a period. And this stays true even if you go to the covering. So if you don't identify points here, you don't identify anymore this point with this one. But if you consider a geodesics, they meet again. They meet again and again and again. So this focusing of the geodesics stays true even if you go to the covering of the manifold. So it's not really a solution of the problem, going to the covering. So now the question is, how do we parameterize the geodesics using the proper time? The idea is this one. Consider the Sitter manifold, the light cone, and the plane which identifies the geodesic. This same plane intersects the light cone in the ambient space along two generatrices. The thing is that we can use this vector psi and the vector eta to parameterize space time-like geodesics this way. Here is, I simply write the solution of the problem, check it. You see immediately that if you differentiate this thing, you get the proper time, dt square. Why? Because these vectors are light-like. So you can easily see that because psi square and theta square is 0, when you square this thing, you just, the exponential drops away, and you get exactly the same thing you had in the denominator. So the vector belongs to the de Sitter manifold. More difficult is to see that this is really a solution of the geodesics equation. And this is the proper time. So what is the lesson drawn from here? If you compare with the way you write the geodesic in Minkowski space, you are willing to propose that these vectors on the light cone in the ambient space play the role of momentum space for the de Sitter geometry. Indeed, you can put this form in this other form using an origin, just one vector on the light cone. So these vectors you see are the direction, the asymptotic direction of the geodesics. So here is the second role the light cone in the ambient space play, is the role of momentum space for the de Sitter manifold. So one exercise I will give in this week assignment is to check that this is a geodesic for the de Sitter manifold. So you can also do the light-like geodesic. And so, because it is momentum space, as you know that the crucial thing to do quantum field theory in flat space are these plane waves, the idea is that these objects are the plane waves for the de Sitter geometry, and we will enter into this. But you can use these things to analyze classical movements on the de Sitter manifold. Indeed, these are conserved quantities. If you compute this quantity by computing the velocity from here, you see that it is not going depending on time. Of course, psi and theta do not depend on time, and they completely characterize the geodesics. So these are the conserved quantities you can build. So here it is, given a geodesics, the 10 conserved quantities you can build out of it. And you can use this to study classical scattering on the de Sitter manifold, because this object is conserved point-like. If you get a point-like scattering, let me show directly in this case. This is the easiest case you can conceive. A particle entering and decaying into two particles. If you construct those conserved quantities I was just mentioning, which are constructed in terms of the light-like vectors characterize the geodesic, they are conserved at the point where the geodesic crosses. And this solves completely the case in which you don't have the angles to consider. In the two-dimensional case, for instance, this you give yourself the entering mass and the outgoing mass, and these are the vectors you get. It's completely solved the problem in terms of these conservation rules. And you see that here, this process can take place at the classical level only if the mass of the entering particle is bigger than the sum of the mass of the outgoing particles. This is the same as in Minkowski space. When we do, if we have time, at the end, the study of the quantum process, the same process but at quantum level, we will see that this is no more true. This is the source of the instability of the de Sitter universe we may have heard about. If you consider one particle decaying into two, one particle of mass m can decay into two particles of any arbitrary mass in the de Sitter universe, and this is because you don't have a positive energy defined everywhere. So you can take out energy from the vacuum.
So how is the mass of a particle defined in de Sitter space?
As the Casimir operator, exactly as in the Wigner way. This is the mass. let's go to this. So plan waves. So if you followed what I said, and you construct this object. So construct this object. Take a vector here on the light cone. Take a vector on the manifold. Take the scalar product in the ambient space sense, and take a complex exponent here. This object, by the way, appeared already in group theory in the work of Harish Chandra, and then in the work of Gelfand. So these are objects which are known to group theorists, and you do the so-called Gelfand transform with this, and the transform in Hori spheres. But what I'm going to say, it's my own work. So to pursue the analogy and the question you were raising, if you do off-shell plane waves, there is no mass here. But if you restrict it on the mass shell, so with the restriction p square equal m square, you can take out the mass here in the exponential, and this is a vector having length 1, okay? The analogy here is with this way of writing the plane waves in Minkowski space. So this lambda is related to the mass, and these waves are, in a sense, already on shell, okay? Lambda is the mass, psi is the momentum direction, exactly like here. M is the mass, and p hat is the momentum direction. So, as I said, these are eigenfunctions of the Klein-Gordon operator on the De Sitter manifold with this proper value. You see, lambda is this lambda here. So you can ask yourself for which value minus this thing is positive, is a square mass. Okay. But by the way, also tachyons exist in the De Sitter universe. So you can observe that there is an involution here. If you consider lambda and lambda bar equal minus lambda minus d minus 1, they give rise to the same eigenvalue. So for a given eigenvalue m square, you have two possible choices, lambda and lambda bar, which is minus lambda minus d minus 1. Okay. So in general, lambda lambda bar is a complex number. But if you are interested in Hermitian fields, you look for real values at least, even for positive values. So there are three possible choices. In the first choice, you parameterize your lambda with a complex imaginary number nu. You write this geometrical number. And you see if you compute it, I will send you the slides. So if you want to learn the sitter, at least do this elementary computation. You see, if you compute for this choice of lambda, so it's apart from this geometrical number is purely imaginary here, the mass is going to be d minus 1 over 2 square plus nu square. So you get a positive mass with the lower bound, which is positive, and it's geometric. This is called, in group theory, this corresponds to the principal series of representation of the Lorentz group of the ambient space. Okay? So you get a first family of theories. You see there is this I in the exponent, which have square mass, which is positive. But what is important in this kind of theories is these are more, what resemble more to plane waves, because there is an oscillation here. These are oscillatory waves, you see. There is an amplitude which is decreasing and an oscillation. So theories which do look similar to flat space theories belong to this family. Unfortunately, you are interested more in theory like this, in which now the exponent is real. So there is a part in the spectrum in which this exponent is real, and the mass is still positive. Now it's d minus 1 over 2 squared minus nu squared. Okay? These are theory which have mass which is between 0 and 0 is excluded, and the same bound. The point is that when you do calculation in inflation, you are interested in these theories. And these theories, unfortunately, you can see this way. If you solve the equation by separating the Klein-Gordon equation in a coordinate system, you don't see this phenomenon anymore. Because, for instance, if you choose the flat coordinate system, you get AEKX times an Hankel function. You think you are right. You are right, indeed. But the point is that these waves are non-oscillatory. They are real waves, just decreasing waves. So this is a quantum field theory which has a feature. We will build the quantum field theory which has a feature which is radically different from what you do in flat space. And indeed, such waves are not localized at all. Not localizable at all. You cannot speak at all about particles here, even locally. There's no oscillation. And also there is the possibility of having tachyons, but I don't enter in this point. So this is the ingredient. So as an exercise, verify that these are solution of they are a proper function of the Klein-Gordon operator. So we are now going to use these things to build quantum field theory. And this is, now that we have done this work, it's in a way trivial. Remember the positive energy way of writing in Fourier space the two-point function of Klein-Gordon field of a given mass in Minkowski space. You construct the same thing in de Sitter space. You get one wave here, one wave here. The complex conjugate of it here is not the complex conjugate, is the conjugate of the exponent, which gives rise to the same mass, but it is the complex conjugate for the principal series. Means when the mass is bigger than the lower bound that I showed to you, d minus 1 over 2, this is just a complex conjugate of this. If you are in the complementary series, this is not the complex conjugate of this. So you see the difference. And the integration, you see that this index psi variable is homogeneous on the cone of degree minus 1, minus d minus 1. So you have to integrate on a basis manifold. This is a differential form which is closed here. This means that you can integrate on every chosen manifold, submanifold on the cone, and the result will not depend on what you choose. Because it's an homogeneous function of degree d minus 1, and there is a theorem by Leray that tells you that you have such a degree of homogeneity, the differential form that you have written is closed. So you can use the Stokes theorem, to deform this integration manifold. Because psi is momentum direction, you just need to integrate over one section of the cone. And this proves the de Sitter invariance of this thing. Because when you deform this way, here you prove invariance by rotation, then you deform this way, you prove invariance by the Lorentz transformation, and by taking any decomposition of your group, you completely prove an invariance. Okay. So let me, this is the Fourier representation, but the point is that how we really go around the problem of getting around the singularity of those waves. Because here we are taking a complex exponent of something that can be positive, 0, or negative. So I need to say something on how gluing together the positive phase with the negative phase. What is the choice? The relative choice of these coefficients. Because there is this opportunity here, you get a lot of possible quantizations. Even a lot of possible de Sitter invariant quantization. You may have heard about the alpha vacua of the Sitter quantum field theory. It is the choice of this alpha and beta. But what I want to tell you is that there is one particular choice in which you get a maximal analytic thing exactly as in flat space. And what you do, you don't have energy, but you remember one thing that I said a few lectures ago, that positivity of the energy is equivalent to analyticity property of the correlation functions. Okay? If you have positivity of the energy, the endpoint functions are boundary values of functions which are holomorphic in regions, tubular regions, of the complex Minkowski spacetime. And this is the base of all the properties of standard quantum field theory. You can do the same. So remember here, this is what I already explained. This is the real space. This is the complex space, two-point function, and this is a pictorial representation of the tubes. This point, you can give an imaginary part to this point, pointing backward in the cone. The blue picture here is the imaginary part. This is the real point, and the imaginary part can be inside here. This is the second point, the same point. The imaginary part on the second point has to be in the future. And you get a maximal extension of it. If you play with complex Lorentz invariants, indeed you see that this is a maximal analytic two-point function. The only thing that remains is the cut, the places where the field do not commute. So you can do the same thing in the de Sitter case. You can take the trace, if you want, or the image, the restriction of the tubes of the ambient space to the de Sitter manifold. These are domain of analyticity on this complex manifold. This is the crucial important point. So you can define these plane waves. Now you can give an imaginary part to Z, exactly as you do in the ambient space, but restricting on the complex manifold, you see? And now there is no more any ambiguity because, you see, this is a pictorial representation of the tube. You see, at any point, not only it has to be in the future tube in this case, but also it has to be perpendicular to this vector. This angle is such that the scalar product of this and this is 0. But if you do this choice, there is no ambiguity in this complex function when you give the imaginary part this way. Why? Because this point is inside the light cone. The psi is on the boundary on the light cone, and you know that the scalar product of a vector which is here with another vector which is inside is positive as a fixed sign, never change sign. You see this. In the light cone, vectors on inside the light cone have scalar product which is positive. And this stays true if one of these 2 points get on the boundary. So the imaginary part of this function has a fixed sign, and there is no ambiguity in this definition. This is a geometry which is a little bit more complicated. Now the tubes, you can do the same thing, exactly the same definitions for anti-de Sitter. You embed in the anti-de Sitter in a complex manifold. Now you don't have any restriction because the ambient space has 2 times, but locally you can see that there are chiral tubes which are defined this way. So if you are on the anti-de Sitter manifold, the tubes have a certain chirality. Locally, the imaginary part goes one way or the other way. Exactly in the same way, these are maximal holomorphic domains. And here is the family pictures. The tubes of Minkowski space, the tubes of de Sitter space, the tubes of anti-de Sitter space. If you choose these analyticity properties, so these are domains of analyticity which are inscribed in the geometry of these manifolds. It is not an external construction. So if you do this way, so choose, this is a choice now. You remember that there's the ambiguity in quantum field theory on curved spacetime. Here I choose to use waves which are the same analyticity property of the waves of the flat space. So if you do this way, you don't have energy, positive energy in the de Sitter case, but you have the same analyticity domain. You can use those domains. What happens? So you get these 2-point functions which are no ambiguity, which is closely analogous to this, and indeed reduces to this when you take the flat limit.
Are they the only ones that do? Reduce to black bandwidth?
I mean, the Sitter invariant, yes. If you allow some more strange thing, I don't know. But if you look into the family of the Sitter invariant solutions, this is the only one which reduces to the, because in between the alpha vacua, which are all the Sitter invariant, they get negative energies in the end. This has negative energy in it when you stay in the Sitter. And that's why I will tell you immediately it is a thermal theory in a certain sense, even if it looks like a vacuum. But if you allow yourself for the whole class of the Sitter invariant theory, and you make the flat limit, you get negative energy in the limit.
So that's the only one that doesn't have negative energy?
In the limit. So now, I mean, if you open a book in quantum field theory on the Sitter space, there are books. Indeed, you will always see expansions of the 2-point function on bases which reflect a particular choice of coordinates. Okay, in particular, maybe you have seen the one which is most used is the one with the Hankel functions in inflation. It is concretely used to compute the spectra, you see. But this you can keep it in mind as you do with this. It's just a Fourier representation. It is the same. Indeed, I will show I will just tell you how you do recover the standard way of writing from here. But you can keep it in mind. Take a wave, in the backward tube, a wave, another wave, in the forward tube, put here the Lorentz invariant measure, integrate on the spherical section of the cone. This is, you can keep it in mind the same way as you do with this. So this is you can take the boundary value and have a 2-point function which is defined on the real manifold. Then you act with Lorentz invariance and you compute it. And you can see that it is a maximally analytic. Always there is this cut in this, the Sitter invariant variable, which is the scalar product of these 2 points, Z1 and Z2 in the ambient space, is a Legendre function, okay, multiplied by this factor that erases a supplement of cut, which otherwise would be here in this function here. And this maximal analyticity, so it has the same structure I described to you for the flat space case. You get one boundary value, you get W. The other boundary value, you get the permuted 2-point function. They are both, they are different determination of one single analytic function. So I will skip the question of positivity. They are positive. They satisfy the positive definiteness one criterion that I told you, to have this quantum mechanical interpretation, you need this. But this is extremely simple now. Because we know that that particular two-point function has this analytic structure, look at it from the viewpoint of an observer, which is very much the analogous of the Rindler observer. Means take your two-point function and write it by using this coordinate system. You can, so you define a time translation, which is defined along these lines here, which is the map T into T plus S here. This is a global time, not non-global, a time-like Killing vector, which is defined in this region. And the maximal analyticity, as you see, if you look at the image of this cut plane, so you need to work with the whole analytic function. The image of this cut plane into, by that, in this coordinate system, this cut plane in that coordinate system satisfies that it is holomorphic in the time variable, and that the boundary values here and here are related by the KMS property. Okay? So this, what is the physical interpretation? Is that in this particular vacuum, when you restrict your field algebra to this region with respect to the time of that family of observer, is KMS. So when you heard the statement that the de Sitter space has a temperature, you have to add all these requirements. If you change the vacuum, if you change the coordinate system, if you don't consider the restriction of the field algebra to that region, there is no temperature in the de Sitter space. It's not something which belongs to the de Sitter space. It's a property of a particular two-point function. When you look at this two-point function from the viewpoint of that observer, you see?
Static observers.
These static observers, yes.
So,
static in the sense that they move on this
along the
killing field.
But are they physical in any sense? If I look at the word lines tangent to the killing field, I find observers that are not geodesic but accelerated.
Sure.
So this is a congruence of observers that
only one is geodesic.
Only one is geodesic.
Sure.
And they all are accelerated.
Except one.
Except one. So this is not what a family of galaxies,
sure,
of freely forming galaxies,
sure,
would record, right?
Sure, but yourself, you are sitting on such a geodesic U, and you are moving in a de Sitter vacuum, which is this one. You being this observer, if you were point-like, you would say there is a temperature. Yes?
I don't quite remember. Is the boundaries for the static black hole patch, I guess you could say, are they time-like, space-like?
The boundaries?
I mean, could information flow through
the boundaries? I mean, the horizons are these lines here.
Oh, so they would be time-like.
Light-like. Light-like.
Oh, wait, sorry, you're right, yes.
Just one word, I add one word concerning how you recover the standard textbook functions. Take these plane waves, use the coordinate system of inflation, that one. Use the same coordinate system on the cone. So parameterize the plane wave by using this coordinate system. Take the Fourier transform of this, the spatial Fourier transform of this. One wave is related to one type of Hankel function, and the opposite wave is related to the opposite type of Hankel function. So one analyticity is H2, and second analyticity is H1. And you will see in the Birrell and Davis book that you have an expansion of the two-point function using these functions here. You put into the Fourier representation that I get to you this little calculation, and you get the standard way of looking at this two-point function from the viewpoint of this observer. In that coordinate, in that representation that I gave you, is indeed this a sort of a summary. If you open the Bateman book in the section in which the Bateman book explains the Legendre function, there are maybe 35 integral representations, which looks different. These are representation of the Legendre function on the form of integral representation that are thought as one point. There is one variable, and you construct a representation. Now, let me go back just for a second to this formula. You see here, this Legendre function here is related to that integral representation as a two-point function representation. This variable z here is the scalar product of these two variables. Now you can play this game, look at all the integral representation you find in the book by Bateman, and try to find a choice of Z1, a choice of Z2, and an integration cycle on the cone that reproduces that representation. You find all the representation. This formula is a compendium of many integral representations of the Legendre function, including the one people use in quantum field theory in inflationary context. Of course, it can be difficult to get one particular representation. It can be extremely easy in other. But this is, I mean, not being tied to a particular reference system. It is a summary of all the possibilities. So let me just tell you that you can do very much the same thing in the anti-de Sitter case. You have the same expression for the plane wave. Now these numbers are integers here, positive and negative integers. I wrote it in an awkward way here. But think that here you put an n, and here you put minus n minus d minus 1. Okay? This is the two-point function. For anti-de Sitter, it has precisely the same form, the same Fourier representation. The description of the integration cycle is a little bit longer. I will not do it. Just I want to tell you that there exists, either in the de Sitter or in the de Sitter case, a way of thinking of this thing which is coordinate independent. It uses plane waves in the ambient space. Yes?
This would be the ADS, where we have the closed timeline curves, right?
Yes.
So we're not using the.
So because there are closed timeline curves, we allow ourselves only integer exponent. But if we go to the covering, we can have any kind of exponent, real exponent in these things. Okay? Because we are not, we want that these waves take the same value after one cycle, we take integer exponents. You mean n is integer? This way, forget about this. Think of n here, minus n, minus d plus 1 here. This is not integer in all dimension, in all space. Take n minus n minus d plus 1, where n is an integer. Okay. So I will flash you now to two applications of the formalism, and then we will end. The first is the ADS CFT correspondence, the beginning of what I understand of the thing, which is a very easy thing to describe. And this gives to me also the opportunity of introducing other coordinate system on the ADS manifold I did not describe, which correspond to the cosmological coordinate system on the de Sitter case, but which are not cosmological here, in the sense that this variable v, that would be a time in the de Sitter case, now it's a space-like. It's a space-like coordinate. You see there is a minus here. This is the Poincaré patch of the ADS manifold, you see, choose these two coordinates in the ambient space, call it exponential of V, you derive this coordinate system. It's very, very easy to do the calculation to cope with the restriction, and you see that this little x is a Minkowski variable. X squared is the Minkowskian square, and you write the anti-de Sitter metric in the form of the Minkowski space-time metric times a work factor plus these transversal coordinates. These transversal coordinates goes this way, okay? This is the Poincaré coordinate system, as it is called. And there are different things you can prove. But one important thing is that I described to you how to select analyticity properties for the endpoint functions on the anti-de Sitter manifold. These are these tubes which have chiralities. When you restrict on the so-called brane, Minkowskian brane, there is compatibility between the notions you use in the anti-de Sitter manifold and the restricted notion on the brane. Means that if you give yourself a theory which is causal in the anti-de Sitter sense and analytic in the anti-de Sitter sense, you get a theory which is causal in the Poincaré sense on the brane and has the right analyticity properties. Means give yourself a theory which satisfies analyticity in these tubes. By restriction on such a fiber, you get a theory which has positivity of the energy. This is not on the boundary yet. It means that you have a theory, someone gives to you a theory in the anti-de Sitter manifold inside, and you take the restriction of this theory on a Minkowski plane, on a Minkowskian leaf, and I want to stress that you cannot do this thing in general, because quantum field theory is a quantum field is a distribution. You cannot restrict a distribution on a submanifold. Why? Because restricting a distribution on a submanifold would mean make the multiplication of one distribution for a delta function. And if you do this, in general, you cannot. Why you can do this here? Because these theories are boundary values of analytic functions. And because they are boundary values of analytic functions, products of distribution in some sense make sense. In particular, you can build all the big powers this way, and you can do perturbation theory because of this. So you see why analyticity is crucial in quantum field theory. Here, in particular, if you give this kind of analyticity properties to yourself on the anti-de Sitter manifold, you are entitled to restrict it on a brane. So the analyticity of the complexification of the fiber is compatible with the notion which is natural in Minkowski. So this means if you give yourself a theory in anti-de Sitter, takes one restriction here, this is an acceptable theory from all the viewpoints on the Minkowski space, which is the leaf. And now you can understand, so one elementary meaning of what the ADS-CFT correspondence is. It is not a correspondence in this way, it's sort of a projection. ADS into CFT. Take a theory, restrict it. You have to take away a little renormalization here, otherwise the limit will not exist, and then take the limit V to infinity. This defines the theory on the boundary. You see, I'm moving towards the boundary, and in the end, I get a theory on the cone, because the cone being projective, I can reconstruct a theory on the whole cone, where is the natural setting for conformal field theory. And the result is that you can prove that if you assume that this limit exists, the boundary theory is conformal invariant. Because you have started from an anti-de Sitter invariant theory, but you need these analyticity properties. Indeed, people, they don't say these things, but they are, when you look at the computation they do, there are such properties. In particular, the very first result by Witt and Polyakov and the others concerning the relation between mass and dimension, you can easily do the calculation this way. This is the two-point function for the anti-de Sitter quantum field theory. It's not the P function, it's the Q function. It's always a Legendre function. De Sitter manifolds are naturally associated to Legendre functions, while Minkowski spacetime is naturally associated to Hankel functions. In the de Sitter case, you have the P functions. In the anti-de Sitter case, you have the Q functions. So if you look at the asymptotics of the Q function, you see that doing this stuff with this on the brain, take out the divergent part, take the limit, and you get a conformal field theory having a very precise scale factor here. So this is the relation mass dimensions, which was in the Witten's paper at the very beginning. Indeed, you can do more than this, but maybe I won't describe this. And here you see these papers by the founders, in which the anti-de Sitter symmetry and the relation to the conformal symmetry was already understood in a way. The names are Klein, Weil, and Dirac. I don't give the description, but it's just geometry, you see. How you embed the Minkowski manifold, a conformal embedding into the cone. These are the coordinate change you have to do. I will send you the slides. And so if you do this, you can even prove more. I mean, you can do, let's say, sort of an axiomatic construction of an ADS-CFT correspondence, even if you don't assume that the endpoint function factorize. You need just to assume the right analyticity properties. If you have the right analyticity properties, and this subtraction works also for endpoint functions, you for sure construct a conformal field theory. It's sort of a theorem here. But I don't have anything to say on the opposite way around. How do you make a correspondence between a conformal field on the boundary and an anti-de Sitter field in the bulk? I don't know how to reconstruct it. But there was a paper by Rehren in which it was inspired by my paper, in which he did some inverse construction.
And in order to construct the quantum field theory, you need also to regularize infinities, right?
I mean,
this construction,
someone gives to me the endpoint functions. This is a theorem in the same way as the PCT theorem is a theorem. Someone gives to you the endpoint functions, which are positive energy, etc., etc., etc. And there is this other hypothesis of dimensional regularity. And then I tell you that first, I can take the restriction to the slice. Second, I can take the limit, and the limit is conformal invariant. So it's a theorem on the general structure. It applies to free theories and gives to you the mass dimension.
What I mean is that in a carved background, carved in a carved space like ADS,
yes,
the quantum field theory.
Just for ADS, because you need you need the symmetry SOD.
Even in ADS, you can. Suppose you have a two-point function, you go to coincident point, it explodes.
Sure.
So the way you extract the finite part.
But I don't go to coincident point. I'm on a brain. I have two different.
Need, but in quantum field theory, you need to do. If you have
What do you mean? I have already the two-point function. Of course it diverges at coinciding point. This is a standard feature. There is, this is not...
If you want to get, if you're going to compute, for instance, in an interacting
sure.
theory, then a finite thing, you have to give this prescription.
But it's not finite. These are distributions. They diverge at coinciding point. There is no problem in this. It's a standard feature of quantum field theory. Advanced, if you want to compute the energy momentum stress.
Yeah, if you compute the tadpole, for instance.
You have the standard things. Sure.
No, the standard thing, what I mean is that you have different way to regularize.
Sure.
And different regularization give you different finite tensors.
If you are looking to energy momentum tensors.
No, the generic correlation function.
Sure.
So the question is, maybe different regularization give you different CFT in the boundary.
But I'm telling you that this is a general theorem.
Yeah, that's
maybe
there's nothing on regularization.
Because it's not a perturbative theorem. It's not perturbative. In the same way as PCT is not perturbative. It's based on the general properties, the symmetry and the positivity of the energy. That's all. We'll discuss maybe later. Yeah. Okay, so this is really a theorem. There is a formulation of conformal field theory which is due to Luscher and Mach in the general setting of this cone, and we proved that you have this thing. And the second, let me just flash this to you. I don't want you to look even to the mathematical details. I was considering this decay in the de Sitter setting, so a particle entering. This is the Minkowskian picture. So unstable particles are described by studying this process. Okay, this is the first computation you do in quantum field theory. Surely you have done it. Now, since you want to do this calculation in curve space, you need to go to the X space formulation. It is possible to do it. So in the end, there is this result. You can express the transition probability in terms of these quantities. First, you need to compute this coefficient C. What is this coefficient? If you take two-point functions and you integrate over the internal point here, over all the space-time, there is a completeness relation that holds in Minkowski space that tells you that this is going to be the two-point function itself times a delta of the mass square, times a coefficient. You need that coefficient. Second thing you need is this weight. This is the so-called Cullen-Lehman weight. What it is, the Cullen-Lehman weight? Take the product of two distributions. Because of general arguments, again, of Lorentz invariance, causality, etc., you know that this object that exists is a product of two distributions. You know that you can't do the product of two distributions. Why you can do it here? Because they are boundary values of holomorphic functions. So this is a boundary value of holomorphic functions. And because of general arguments, you know that you can expand these products as an integral over all the masses. A is a mass with the weight that depends on the given value of the masses. This is the so-called, this is true in general, whatever you put here, which is Lorentz invariant and analytic. This is in particular true for this true product of two things, and you have a weight that you need to compute. This is also called in the books of quantum field theory the phase space factor. And here, this is how you did prepare your initial state. You see, this is a positive frequency solution of the Klein-Gordon equation. A test function, you average over the two-point functions, you get a solution of the Klein-Gordon equation, which is how you did prepare your initial state. So this is what you need to calculate. In the de Sitter case, you can see that this projector identity I was mentioning, it is true for the principal series, does not hold for the complementary series at all. you get here a divergence which cannot be curved. It's an infinity you cannot throw away. So you see here a difference between the principal series and the complementary series. And the complementary series means masses which are below a certain mass, while principal series masses which are above that mass. Unfortunately, the theory which are interesting for inflation are in the complementary series. So they are difficult. So how do you compute this weight? Here I put how you do in the standard flat space case is an exercise in Fourier transformation. And you see that there is a step function in the end. This means that decay cannot take place if the masses of the two outgoing particles in the sum are bigger than the entering mass. Okay, I'll send you the slides. Verify this calculation. This is an instructive exercise in Fourier transformation. So you see, for equal masses, it's extremely simple. It's a certain thing, certain prefactor which is geometric. This calculation was done, I think, by Fermi on the back of an envelope with his own methods to compute the decay of the pion. You see? And there is this theta functions that conserves the energy. It's the energy conservation. Now you need to do the same for the de Sitter case. In the de Sitter case, you don't have the Fourier transform. So you have to deal in the end with such a thing which is called the Meller-Fock transform. In this integral, you see three Legendre functions I was mentioning to you the other day. One of them is the kernel of this Meller-Fock transform, and the other two are the product of the two-point functions you want to transform. So if you compute this, which is difficult to do, you get this weight. You see, it's interesting already. This is a product of 4 gamma function, but you already see that it never vanishes. It's an allomorphic function, the gamma functions. So you already see here that one particle can decay into 2 of arbitrary mass. Let me tell you the things I was telling you to you yesterday. This is the formula which was in the book, which is wrong. It's in the 3rd volume of the book, Prodnikov. I tried to compute this thing for years. It took me 3 years to do it. Not every day, of course, but I was thinking of this problem. One day, I believed that I could solve this problem, calculating this thing, for the special case in which the dimension is 2. Because computing this integral is difficult in even space-time dimension, is easy in odd space-time dimension. In odd space-time dimension, it's just an integral of sines, cosines. In even space-time dimension, you don't know how to do. One day, I thought that this formula was one way to compute it in the two-dimensional case. Unfortunately, this formula is wrong. But the very strange thing is that it gives the correct results, even if it is wrong, because the imaginary part of this formula, in some sense, is correct. So I wrote to Marichev, and he told me that he knew the formula was wrong. So don't believe formulas you pick in books concerning integrals. So here is the proof, but it is more interesting to examine it another way to do this proof, so you can see how this plane, where and how the plane waves can be useful to do concrete calculations. So if you think of the two-point function in its maximal analyticity domain, you can put one point in the back tube with no real part, and the second point in the forward tube with no real part. I'm considering not the Euclidean section, but the purely imaginary section. You don't have anything like this in flat space. Because you are on the de Sitter space, there is a boundary in your analyticity domain, which is the purely imaginary points. Okay, you can see this sort of boundary here. So this you can use in putting in the two-point function I showed to you, and you get this representation for the Legendre function. You see, this is the plane wave, but in which y is a point which is now in the Lobachevsky space. Psi is on the sphere, is an average on the sphere of this wave. Is another new integral representation you don't find in the books. So what is the advantage of this thing? Is that you have expressed this thing as the integral of a plane wave. So we are going to transform an integral in one variable. You can think that this is not a very good idea. This integral is in one variable. Now it has becomes as an integral over d times d minus 1, d minus 1, d minus 1 variables. But this is a Fourier integral. You can try to do it. Okay, so this integral, you don't know what it is because you are not obliged to know by heart the definition of Legendre function. As b transformed into a Fourier integral, these objects, you know what they are. Y is a point on the Lobachevsky space. Psi are 3 points on sphere. And you have to integrate this thing. This thing, by the way, opens also the way to a class of integrable models that have not been yet studied. Indeed, you can act with the star. You can now play with the symmetries. There's the star triangle identity. Because of the symmetry of the Lorentz invariance of this integral, you already know that the answer has to be in this form. So it is function of the invariance, psi1, psi2, psi1, psi3, c3, c1, to certain exponents which have to be compatible with the degree of homogeneity of the thing. So in the end, you have to compute this average. This is the last step you have to do. And if you look into this, you see that there is behind this a probability measure, rho. And these are the moments of a certain probability measure. All this you discover when you start playing around with these plane waves. It's already inscribed in the geometry. You don't need to invent anything. Of course, the computation can be difficult. It is more difficult than in flat space because you don't have translation invariance. And translation invariance is what renders things in quantum field theory possible to be computed. Here, even the easiest calculation has to struggle with the lack of translation invariance. If you do, so it's an hard job. It took 4 years. This is the final answer that I think is nice. You don't find this formula in the Gradstein book, in no other book. It's the integral of 3 Legendre functions. We see these are the masses of the particles involved in the process. And this is simply this thing. It's quite, I find it nice. I don't know if you find it nice. It's the product of 8 gamma factors in which the masses you see enters with all the possible signs, plus and minus, all the combination, over the product of 6 gamma functions of separated mass, you see? Here you are going to, but even I can stop here because this result tells you what I wanted to say. Because this weight is nowhere vanishing, one entering mass can decay into 2 masses arbitrarily large. Of course, it's exponentially suppressed, this thing, but it's possible. While in Minkowski space, this is just impossible because of conservation of energy. And one thing which is really amazing to me is that if you compute the flat limit of the rho we have computed this way, you get the Minkowski answer. Why for me this is surprising? Because you can think fastly thinking that locally the sitter should be like Minkowski. But this is not a local quantity. I've integrated many times all over the manifold, the whole manifold, not just in portion of it. And in the end, taking the limit, I got back the Minkowski result. I think it's a surprise, but I don't know if you think as a surprise. So my point, to summarize what we said during this course. As much for de Sitter anti-de Sitter. Let's make a final summary of what we said. What we said is that there's a structural difference between quantum mechanics and quantum field theory. This is the fact that this is because quantum mechanics describes systems with finitely many degrees of freedom, and quantum field theory describes systems with infinitely many degrees of freedom. So this, you cannot do anything against this thing. When you study quantum field theory, and you study it on a globally hyperbolic manifold, and you study free theories, linear theories, which are, by the way, the ingredients of perturbation theory, there is one quantity which is uniquely selected by the geometry. It is the commutator. But if you want to really quantize the theory, you need the two-point function. And here, the choice of the two-point function is arbitrary. What is arbitrary in the two-point function is its symmetric part. The anti-symmetric part of the two-point function is fixed by the commutator. The symmetric part is arbitrary. You just need to produce a symmetric part which is in agreement with the positivity requirement. Any possible choice is good. Of course, it's good for what? If you want to do perturbation theory, you need something more. You need the possibility of renormalizing the theory. So you need, for instance, theories which have the local Hadamard behavior. This is in some sense common sense agreement of everyone. So they have to behave at short distance as if the space-time was flat. Okay? But in this particular category, we find the vacuum and the KMS theories, for instance. But one common feature of all this quantization is that they are always, more or less always, related, the physically interesting choices, to the analyticity properties of the correlation function. This is true for the most important theorem of flat space-time quantum field theory, in particular the PCT theorem or the Bisoniano-Wichmann, or all these theorems are heavily using the analyticity properties of the correlation functions. For the de Sitter anti-de Sitter case, in both cases, at least for free theories, we can reproduce quantization which have exactly the same analyticity properties, but of course, the domains are curved now. So the difficulty is the lack of translation invariance of these domains. But the physical interpretation, either in the vacuum or with temperature, is always related to analyticity properties of the correlation function, and this is the summary of what I said. Okay. If there are... I'm not supposed to upload on a course. Okay, so thank you for coming, and hope it was not completely useless.